You're just joining us, you are in the data track. We have two other tracks going on with two other sessions going on in parallel. So if you want to check those out, you can click on the agenda tab. And before we go on to the next exciting session, we just have a quick poll for you. So if you could go on in the polls tab, that's just asking us how you're liking the event overall. And then of course, we're doing polls at the end of each session, just asking session specific feedback from you as well. So if you could just take a moment to do that, we'd really appreciate it. And with that, I am super excited to announce our next speaker. Our next speaker is here to talk about Landing Lens, a journey in democratizing AI. We have engineering manager from Landing AI, also one of the earliest employees there, Dylan Laird. Hey, Dylan.
All right. Can you hear me?
Yes. Thanks for being here and joining us today.
Perfect. Yeah, thanks for the introduction.
Of course. And for the audience, just while Dylan's talking, just add your questions in the Q&A tab, and I'll be back here at the end to ask those questions to Dylan. So with that, over to you. Thanks again.
All right. And just to check here, just want to make sure my slides are showing.
Tell you if they are not. Okay.
Do I have to click anything? Sorry.
I think so. Well, I mean, I think we have it, so I could actually share it, and then can you?
Oh, there we go. I can click on it. Perfect. All right. Thank you. Sorry about that. All right. Hi, everyone. I'm Dylan Laird. I'm an engineering manager here at Landing AI, where I lead the machine learning team. And today I wanted to give a presentation about Landing Lens, which is our main product, and kind of the journey we went through in developing that product, and some of the both data-centric approaches we've incorporated in there. All right, so just for some background, what is Landing Lens? Landing Lens is a ML platform that we built, and it enables our customers, oftentimes non-engineers, to be able to use AI to solve their problems. So these are, kind of people in different industries who have these real-world problems, such as, a manufacturer who might be wanting to, build an AI system to inspect defects or things like that. And so just to kind of give some more description of that, what are our customers and kind of what are their objectives? And so they're kind of customers all over the place. I mentioned manufacturing is the main one we work with. There's agriculture, pharmaceuticals, but often we found that they kind of have three sort of objectives that they're trying to work on. So one is reduce inspection costs. Right. So if you're a manufacturer and you're producing an item, you got to pay for a system to inspect that item for defects. You don't send them to, you don't ship defective products. And oftentimes that inspection process is pretty costly. So if you can automate that with a machine learning system, you can kind of reduce that cost. Another objective is often improving quality. So this could be decreasing false positive or false negatives. False negative being an item comes in, it has a defect on it, and you accidentally classify that item as okay and ship it to your customer. So you obviously don't want to do that. And then kind of a third objective is a lot of our customers actually already have ML systems, but they're pretty costly to deploy, or they might have a very high false positive rate. So they're flagging a lot of products as defective when they're actually not, and it causes them to have to reinspect the item again. So reducing this cost and making this process a lot easier. So that being said, how did we initially kind of approach these problems with our customers? So we didn't start off with the platform. The first thing we did was we kind of focused on one vertical. In this case, it was manufacturing, and we actually ended up, building custom solutions for our customers. We kind of initially thought this was going to be a really easy problem to solve, which it was not. And so, in doing so, we quickly started to find all the difficulties with doing this and developed processes for quickly completing these projects. And we also started to build some of the initial items that would later kind of evolve into the platform, such as labeling tools, modeling framework for training our models. So, as we were doing this, we started to very quickly run into big challenges, particularly in this manufacturing area. One of those challenges was ambiguous labels. So oftentimes you're working with a manufacturer who, they might have an inspection process and they're actually looking at the physical part to determine if there's a defect. Obviously, if you move to an automated system that uses machine learning, you're going to have to move to digital images instead of looking at the physical part. And that you lose a lot of information there. So what happens is you kind of end up with a lot of weird looking side cases, and you're not exactly sure if this product should be okay or if this product should be not good. So that was one of the problems. Another problem is very small data sets. And you have these for two reasons. One is your manufacturer. You're not trying to produce defective products. Therefore, you do not have a lot of images of defective products. And the other problem is it takes a lot of resources to label a lot of images. So we don't have these like million image data sets that, that you see in academia or at these big companies. They're typically in the hundreds or thousands of images. And then another problem is, for customers who kind of have machine learning solutions already but want to improve them, there's very slow time to deploy. So there wasn't really best practices for how to get something into production, how to make sure that it's working correctly, how to even like iterate on the model initially to get it to the right performance. So to solve these problems, there's kind of two big breakthroughs that we sort of developed. I'm sure you guys obviously developed data-centric AI techniques in your own kind of ML life cycles and your own problems, and so I'm just talking about what we kind of worked on with these manufacturers. But one is the ML life cycle. So this idea of kind of breaking it down into three stages: data, model, deploy. And then very important, being able to iterate from that training model back to the data, or the deployment back to the training model, or the data part. And then the second item here that Andrew Ng has talked about quite a lot is the data-centric approaches. So when I'm analyzing the model results and I'm going back to that data section, what exactly am I doing? How am I modifying that data to improve the model performance? So the idea of this life cycle actually came from a book Andrew wrote called Machine Learning Yearning. And if you haven't read that, I strongly encourage you to check it out. I think it's chapter 10 in that book. He talks about the iteration cycle of building a machine learning project. So oftentimes you start off with an idea, and then you code up that idea, and then you run an experiment. And then from that experiment, you analyze the results and you come up with another idea. And what we found out was, after kind of building the main code base, we actually weren't going back to code so much as we were going back to modifying the data. And so kind of updating this life cycle here to go from idea to data to experiment was kind of the beginnings of what we started to see as this life cycle. And if you look at some of our earlier projects, the time allocated to different parts of that project really reflects that life cycle. So, this is a particular project, took about 2 months to complete. When we started off, I think we were building some initial code bases for training the model, maybe analyzing the data. But your first, objective is kind of building that defect book. So I talked about ambiguous labels before. You really want to figure out better label definitions early on so that when you label the data, it's labeled correctly. And then obviously after you finish that defect book, you're going to start labeling the data. And then once that's finished, you're going to start your experiments. And then even after running our experiments, we found that instead of updating, hyperparameters or trying new architectures, we were going back and updating the data, finding a lot of mislabeled data, finding a lot of like added distribution data that we had to, figure out what to do with. And then obviously there's some coding before you deploy there. And so, if you kind of looked at how much time we spent, it was about 50%, sometimes or oftentimes more now, that we spent just looking at the data itself. And this was super important because we actually looked at, we took some of their inspectors in this case, and we asked them to, label the same set of data. And we found big discrepancies between what they were seeing as defective and not. So in one case, this person had 0 escape. Escape is like a ratio of false negatives. While another labeler had 30%, and we were targeting near 0% escape. So, obviously starting off with those kind of definitions, we would never be able to achieve the objectives we wanted to. And so coming off of these projects, we started to piece together a very detailed sort of outline of how we wanted to do these projects and what we could do to make them efficient. We called this the AVI ML lifecycle, AVI standing for automated visual inspection. And this was often how we would go through projects. So you first scope out the project, evaluate the ML problem, and then you move into the data section. Data section often starts with setting up the imaging solution, which is extremely important. If you don't have the right resolution, you don't have the right lighting, you're never going to be able to get an ML model to classify those images. And then you go on to setting up the defect book, labeling the data, and then you start to move into model training and error analysis. Error analysis is analyzing the errors that a particular model had. And there's some key kind of loopbacks here. So from error analysis, you can see we call this line here model iteration. You're going back to labeling data, right? So we're oftentimes going back to update the data to then improve the model results. And then obviously you've got we call this continuous learning, which is the deployment part of that. And then from there, I think Andrew actually kind of did a really good job of simplifying this down into sort of like 3 main constructs. It's your data, your model training, and then your deployment. But this kind of wasn't the full picture yet, right? So the tricky part here is, well, how do you, this blue lines that, are these lines that go back to collecting data. What do you do there? How do you, what do you do with the data to improve the model results? And I'm actually not going to spend too much time on this part because I think Andrew's got a really great talk called Data-centric AI Real World Approaches, where he lists out 5 tips. But these are tips that we would use in our projects. And I'll talk a little bit later about how we incorporated some of these tips into the platform. But just to name a few, using consensus labeling and running this kind of error analysis on subsets of data were pretty key to our problem. So what was going on here? So we were doing these projects manually, but obviously this wasn't a very scalable approach. So we can't hire a new machine learning engineer every time we want to work with a new customer. On top of that, while we had a code base, we were producing lots of non-reusable code, right? So for each project, it was slightly different, which creates a lot of maintenance work. And then, while we were able to get some of these timelines down to 2 months to complete these POCs, it was actually still too slow for what our customers wanted to do. So we really needed to speed that up as well. And so that kind of brings us to our second approach here. So that's when we really kind of went full on board with this platform idea, right? We really wanted the platform to be able to solve or take care of that ML part for our customers. If you remember before, our customers are not necessarily machine learning engineers, so that you don't want them to have to deal with the ML part. We also wanted an all-in-one tool, right? So you have this labeling model deployment part, but we don't want our customers to have to chain labeling with their own modeling code and then use another library for deployment. We kind of want it all in one. And then finally, we want to make them self-sufficient. So we don't want them to have to learn like a whole new field of ML or how to, figure out mislabeled data on their own. We want to, provide as much context as we can for them. And so you can kind of see if you ever get a chance to try out the platform that these are kind of the main components of the platform, right? So there's three main tabs. You have your data, model, and deployment. They're really developed from that life cycle. Also, some of the tips that Andrew talks about using consensus labeling is a core feature of the platform. So having multiple subject matter experts label the same data and figuring out very early on where they're matching up and where they differ in their opinion, right? And spotting those quickly on or early on. And also the tip 5, so using error analysis. So we've got, it looks like these are just where they're not getting loaded. Anyways, you can click into a section there and you can analyze different slices of your data. So trying to figure out, hey, in this particular data set, what are my false negatives? And you can go back and look at that data and, relabel it and fix your data problems. So, what was kind of the outcome of this? Well, if you remember before, our manual approach was taking about 2 months, some high variance depending on the project, but roughly 2 months to complete a project. And then the platform, we've been able to do essentially the same amount of work in 2 days. I mean, you just do not have to code up as much. It's much more streamlined. You're going directly from model results back into updating your data. But there was still some ongoing challenges here. So we weren't, totally out of the water. One of the issues was if you looked at a graph of time versus solution quality, where solution quality, could be accuracy or precision or recall of your model, our customers were still it was taking them a long time to get to the solution quality we want. And we also had to help them out quite a lot along the way. And if you looked at like our MLEs on the same project, they were sort of reaching this quality a lot faster. And what we're finding out was, these customers they're not MLEs, they're people who have the real world problems, in manufacturing or agriculture. And they're not as, they just don't have the knowledge to iterate on the model like an MLE might. And kind of, if you don't know about how to read loss curves and you don't know about, kind of how models learn and what to look for in terms of issues with data, you can get stuck early on, right? If I hit train, if I label my data, I think it's good. I hit train and all of a sudden I get like, 10% accuracy. I don't really know what to do next. Whereas an MLE might, oh, your loss curve's off. You need to, bump up your augmentation or something like that. On top of this, we're a cloud-based platform. The slower iteration can also kind of cause really slow feedback. So if you can't in one sitting hit train and see your model results and then update your data, you're probably going to leave, come back an hour later. It's going to take you a very, very long time to iterate on this, especially if you're not making kind of optimal decisions per iteration. So to solve these problems, a little bit funny, we actually had to focus on the ML side of things instead of the data set side of things. But we really wanted to do this so that our customers didn't have to focus on the ML side of things, so they could look at the data part. But that was kind of two main objectives there. One was we have to have faster iteration. You can't have people, not being able to see the results in one sitting, and you have to have good out-of-box performance, right? You can't have a side case where a customer trains a model and they, oh, you should have run for more epochs, or you should have tuned this hyperparameter. So on the faster iteration, like I talked about before, you couldn't really in one sitting hit train and analyze the results. And this can, cause exaggerated slowdown, right? Like if it takes you 20 minutes, you're not going to wait there for 20 minutes for the results to pop back up. You're probably going to come back 30 minutes, an hour later. And that could be the difference between, making 3 iterations or 5 iterations a day versus 1 iteration a day. And so we kind of worked on a lot of different aspects to sort of quickly, improve that speed. So going from like 20 minutes to less than, a few minutes. And I can't talk about the specific details here. So going to the next slide. Because it's kind of internal IP, but you really, in a cloud platform, you want to focus on two things, right? So your infrastructure, and then obviously your training time. Your infrastructure is how do you keep costs down, right? Do you get a big beefy GPU, or do you get very small GPUs? How often, how long do you keep them warm, right? That costs money. Can you spin them up really quickly? And then on training time, it's not just about speeding up training, but I talked about that out of the box performance. How do you speed up training while maintaining performance? And there's a lot of literature on this area. So you can kind of guess what we ended up doing there. So like I talked about before, Andrew has this slide where he talks about how AI equals code plus data. And if you're good at the code part, like an MLE is, you can really focus on the data and I think make meaningful improvements. But if you're not, if you don't have that ML knowledge, that code part can become a huge bottleneck for you and can really slow you down. So it was up to us to kind of improve this. So, we're looking at kind of our customers' projects. If you look at accuracy over the frequency of them getting that accuracy on the first iteration versus the second iteration, like I said previously, if you get bad performance initially, you're going to get stuck, and you're not going to know how to improve that. So what we really needed to do here was kind of go case by case and look at all the different side cases, what kind of data our customers were running on, what kind of labels they had, to try to build a better out of the box experience. And that kind of fell into three areas. The first is auto tuners, right? So is there anything I can do to look at that data ahead of time and figure out what I should set the hyperparameters to so that you get a good kind of initial experience? The second one is safeguards on hyperparameters, right? You need some adjustability on the hyperparameters, but if I, for example, offer you a tool to adjust the brightness for, as a data augmentation, you probably do not want, pure white images going to the model. It's not going to help out, or dark images. So setting up kind of sane safeguards on those hyperparameters. And then the other one was better default parameters. You get these models from academia, and they work really well on ImageNet, but we are so far away from the ImageNet distribution that they just do not transfer very well. So really trying to work with the data distributions that our customers have, the data set sizes our customers have, and making sure that those models work well for that type of data. And in doing this, you kind of eliminate that whole coding problem for the customer. So through the platform, they can be better at that algorithm part. And because of that, they can now spend more time focusing on the data, which is really where they are the real experts, right? They look at this data all the time, and they should be kind of imbued, embedding their knowledge into that data set and the labels. So quickly, kind of just to summarize here, initially we kind of developed this process, this ML lifecycle with these three main steps. Andrew talks about this data-centric approach. We tried to embed that into the platform to help guide our customers to use data-centric approaches to go through this cycle. We also want to ensure that they can go through the cycle quickly, so they're not getting bottlenecked on the training process, right? And finally, we want to make sure that they're able to step through without getting stuck either, right? So if you have a bad performance out of the trained model, you can't go to the deployment. So how do you, make that initial experience a lot easier? And then finally, while we've worked on these problems, there's still a lot of big remaining open problems that we have to still try to tackle. And there's lots of literature on these in academics, but again, kind of taking that and transferring it to the data sets that our customers have is its own challenge, right? So one of those is small data. I talked about how they don't produce defective items, but they definitely need an automated system to capture these defective items. So how do you deal with that small amount of data there? Automated labeling, right? Labeling is a big problem for our customers. They don't have huge labeling teams, and they don't want to spend a lot of money on labeling. But DL is a very data hungry type of machine learning solution. So how do you increase the labeling throughput? And then finally, continuing to help them find data issues automatically, right? So it's still a bit of a struggle to figure out, oh, should this label be, in this position, or should I cover this defect here and not this, similar looking thing here? So how do we automatically detect these issues in the data for the customer? All right, and that is the end of my slides. Thank you.
Amazing. Thank you so much, Dylan. I mean, it's exciting to see all the iterations that you've come through. I mean, I know when I worked there, we were at the first iteration, so sort of it was good to see that live, but it's exciting to see also the progression. I mean, we may have time, like 2 minutes for questions, so I'll just ask a couple. So the first one is, people are really liking that you have that speed up in terms of, I think you mentioned 2 days somewhere, but in general, how long does it take for your customers? Let's say if they're starting from scratch, defining, the type of defects that they want to do, et cetera, to getting to a model that they are happy with? Like, how long is that time generally?
Yeah, that's a great question. It's highly variable, I'll say that. So it can be 2 minutes, given that you have the right imaging set up, and you have a good sense of what types of defects you want to identify. So in that instance I gave there, they already had a good imaging setup, and we had that all sorted out. But it can definitely take longer, right? So if you don't have the right camera set up, oftentimes you got to hire a team to set up that camera to take images of the defects to make sure that you can identify those properly. So obviously that process itself can take a couple of weeks to a month or more. But once that's done and you're in the platform, we do generally see it in less than 2 weeks.
Nice. Okay. Awesome. One quick question, because I know we're almost there, but we have a question around what data type or modality are the most challenging. I know you mostly work with images, so I guess a better question framed might be like, what sort of types of defects or types of products are the most challenging to work with?
Yeah, that's a great question. They can all be challenging, but I'll just talk maybe a little bit about some of the key differences between the general data distribution that we work with versus the ones you see like ImageNet. So one key difference is our images are typically a lot larger. You have a lot of customers, they're not all larger, but a lot of times you do have customers, they have these big cameras, and you're looking at, especially if it's an electronic device, you got a pretty big image. And then the second kind of key aspect there is your labels, or the defects you're looking at, are very small. So not only do you have a huge image, you got a really tiny defect that is maybe 4 pixels by 4 pixels on that image that you have to detect. And so you can think of all the challenges that causes.
Makes sense. Definitely. Also, in the contrast between the defect, I imagine, like, when we track it on lenses, like that's just like really hard for a human to see, let alone a machine or like an ML model. Anyway.
Yeah.
So, unfortunately, that's all we have time for. If people did want to ask you more questions, what would be the best way to reach you?
Yeah, I think my Twitter. Either Twitter or LinkedIn. I don't check quite as often, but probably Twitter or email or LinkedIn. Anyone.
Reach out to Dylan on Twitter or LinkedIn. Amazing. Thank you so much, Dylan, for being here with us and sharing this journey of landing lens.
Awesome. Thanks for having me.
Bye. Thank you. Yeah. For our audience members, if you could just take a quick second to go to the polls tab, you should have gotten a notification as well, and just tell us how you thought that session went. Just helps us plan future sessions as well. Just take a quick second or two to do that. We really appreciate it. And then up next, apologies, I was sharing Dylan's slides, so just 1 second. Okay. Up next, we have a very exciting talk in the data track around NASA's Space ML Worldview Search. And again, you're in the data track. So we do have 2 other tracks going on right now, the techniques and the application track. So go to the agenda tab and you can navigate to the other 2 as well. But if not, I'll see you in a little bit at the NASA session. Thank you.